Uh, so I sent you an announcement about the final exam date. So I think because someone asked me about it last time, I think in your schedule, on the official site where you check the schedule for the exams, it says that the final is on the 8th, but it's actually going to be on the 2nd. So you take it on the same time date as all the other multivariable sections. So which is on the 2nd. So I sent an announcement about it from 4 to 7, and the classroom, I don't remember, but it's on the announcement on Canvas. But like the important thing is like the date itself. So it's more or less like 3 weeks from now, from today, well, because it's on a Thursday. So I think by there, like probably by tomorrow or Friday of this week, I'll post like kind of like the study guide for the final and the practice exams for the final. And we can talk more about the final next week, but at least that way you'll have like an idea about what's left. But yeah, I figured I should like just start like mentioning this because it's kind of important that the date is different from the one you would see on your schedule. Okay. And as I said, I hope to have finished grading the exams by tomorrow. So once I have done that, I'll send you an announcement and I'll post the solutions as well. So let me do another example about integration in spherical coordinates and cylindrical, and then we'll switch topics a bit. So kind of in the in terms of like the difficulty of the remaining topics, like triple integrals is one of the hard topics, so it's kind of like a local max. Then like the difficulty does decrease a bit, which is what we'll start talking about today. Like the next few sections of the book are are relatively easier compared to what we have been discussing. So this is like kind of where like all this stuff about work, potential functions, Green's theorem goes in. And then there's another local max at something that's called flux and surfaces, which are, it's kind of almost like the last topic, like the course. But basically, yeah, spherical coordinates especially tends to be one of the tricky topics in this course. And then we'll have like a few sections which you'll see are way easier compared to that. And yeah, the last 2 or 3 sections of the book are also kind of can be a bit confusing. So, but we'll enter this period of like relative calm between those 2 peaks. So let me do another example of triple integration, which will reappear because also they will be used for the last stuff of the course. So like we'll talk more about triple integrals later. But I figure I should at least do another example to kind of emphasize like this thing about doing the cross sections. So let's find the volume. Triple integral. I'll do it in cylindrical and spherical so that again you can compare how the two look. So in cylindrical. Spherical coordinates. Which gives the volume of the region inside the sphere. And above and outside the cylinder. This is the one that I want to use, yes. Let's see. Let's start by drawing everything, which again, is my recommendation for all these problems involving integration, whether they're double integrals or triple integrals. It's useful to have like pictures of everything. So this is a sphere center at 0, 0, 2 of radius 2. We're 0, 0, 2. That's how the sphere looks like. We did this last time, but remember that you can rewrite this by, so if you rewrite it in cylindrical, it becomes r squared plus z minus 2 squared equals 2. And if you rewrite it in, sorry, it should be a 4 here. And if you rewrite this in spherical, okay, so you get a rho. I think this is what you get for cosine of c. I think that's what we had done last time. I can double check it quickly because this is like r squared plus z squared minus 4z plus 4 equals 4. So the 4's go away, r squared plus z squared ends up being rho squared. So you get rho squared equals 4z. So rho squared equals 4 rho cosine of t. If you remember how spherical coordinates are defined, and so that's how you get that rho equals 4 cosine of t. Okay, so that's fine. So remember from spherical, maybe I should just remind you that z equals in general rho cosine of phi. That's really important. The other one that's really useful in practice is like the relation between r and rho and phi. Okay, so those are like the two main equations that you should remember when you do spherical coordinates and you want to relate that to cylindrical coordinates. From there, you can find like most of the things that you would ever need to. So I'll raise this in a bit, but let's just leave it like that. So that's the sphere in Cartesian, in cylindrical and spherical. Okay. And then what is this cylinder? So this cylinder has radius root of 3. It's a bit slightly, it's almost the radius of the sphere, but it's a bit smaller. So it will look. It looks something like this. Okay, so that is the cylinder, x squared plus y squared equals 3, which again in cylindrical becomes r equals root of 3. And then using that r is rho sine of phi, that's why I was saying that this equation is useful. If you use that r is rho sine of phi, that allows you to find the equation immediately in spherical, which is that rho equals root of 3 over sine. Is that okay? So that's why really these two are particularly useful. Um, Now, what happens here is that if you look at any of these two, like if you look at both of the equations, oh, by the way, I should color this. So the region of integration that we're discussing is the stuff inside the sphere, but outside the cylinder, right? So let me color that for you. So we're trying to find the volume of the purple region, which by the way, looks kind of like two separate pieces, but it's actually like a single piece, right? Because like the, it kind of goes on behind the board and in front of you, right? So like, it's just like, imagine like having a ball and there's like a tube going through the ball, like a slightly smaller radius. So, everything is connected. That's what I'm trying to say. Like the two purple regions are connected. It just looks like separate, but that's kind of like an illusion of the picture, if that makes sense. So it's like a single piece. So we're trying to find the volume for this purple region. Now, what I was saying last time, and this is like the nice thing about these problems, like that we're working with, is that these equations have symmetry, which means that if you start rotating the picture about the z-axis, it's like looks exactly the same. In terms of the equation, the symmetry is present whenever there's no theta explicitly. So what that means is that um, instead of finding the bounds of integration directly from this 3D picture, you can just find the bounds of integration from like the cross section. Okay, so let's draw that somewhere else. So if you wanted to find the bounds, what you can do instead of drawing the picture in 3D is just draw something that I called last time the RZ plane. So you keep Z as the vertical axis, but now you call the horizontal axis R, okay? And what happens if you do that, then the equation of the sphere is this equation, right? But then now the thing is that Z is like the vertical variable, so it's kind of y, like y, and r is a horizontal variable or the horizontal axis, so it's like x. So this is almost like x squared plus y minus 2 squared equals 4. So it's really like the equation of a circle on this plane. And again, I'm only going to draw half the circle because for us, like r is always a negative. So that's the most that you need to draw here. And so oops, like, sorry, this is like center at 0, 0, 2, so I'm drawing the wrong circle. The circle looks more like this. Now this is fine. Okay. So that's kind of how the circle looks like. So that's the center that I'm putting here at height 2. And then the the cylinder, which is r equals root of 3. Now r is like x, so it's like x equals root of 3. So that is just x equals root of 3 would be like a vertical line, so it looks like this. And from this perspective, it's easier to see the region of integration. The region of integration corresponds to this purple region. And the idea is that because of the symmetry, if you were to rotate this about the z-axis, right? You start spinning this around, you will recover the entire region in the actual 3D solid. But the advantage of doing it this way is that it will finding the bounds will look like finding the bounds for like a double integral in Cartesian coordinates. So it's a kind of a double integral problem, basically. What you end up getting here. Is that making sense? Questions about that? So let me do the bounds first for spherical so that you see how they look like. So remember, I think I mentioned this once. If you want to find the volume using a triple integral, to find the volume, what you should do is integrate the function one, because then it's kind of like a sum of just all the little volumes here, like the volumes of the mini boxes or whatever. So this is true in general. Okay. It's just that dv, so if you do the integral first in cylindrical, dv is r dc dr d theta, right? So put here r dc dr d theta. Okay. And so again, if you ignore theta, you have d z dr, but z is vertical and r is horizontal, so it's like saying these dy dx. So it does look, basically finding the bounds here behaves more or less like finding the bounds for like dy dx when it was like a regular Cartesian integral. So to do that, we just look at the, you want to find z bounds. So the z bounds, like if you look at these arrows, they go from the circle to the circle, actually. So the idea is to use this equation to solve for this, for z. So you can take z minus 2 squared equals r4 minus r squared. And then after taking square root with plus or minus, you get z is plus or minus, is 2 plus or minus the square root of 4 minus r squared. So the minus solution is the lower bound and the plus solution is the top bound. Does that make sense? Like how I found that? And then what are the bounds for R? Now finding the bounds for R is like finding the bounds for X, if this were like a regular double integral in Cartesian. So the X, like if I can think of R as being X, so like you would have said X goes from the yellow line, which is at root of 3, to wherever this circle terminates, right? And the circle terminates at 2 because this has radius 2. So the bounds for R go from R equals 3 to, sorry, R equals root of 3 to R equals 2. So here is R equals 2, right? That makes sense? Yeah. And finally, the theta bounds are not shown in this picture because again, theta is kind of like the variable that's being used to spin the entire 2D region. So theta is not in the cross section. So theta here is just like represents like what's the angle of rotation that you need to recover the entire region. So theta goes from 0 to 2 pi, right? Because if you rotate like the entire cross section by 2 pi, you get back the solid. And so that would be the volume in cylindrical. I mean, that would be the triple integral in cylindrical that gives you the volume. Is that okay? Make any questions about this? Okay, let me do it in spherical. So I'll redraw. I'll write again the picture because now I'm going to work with the bouncing spherical. So let's put here R and Z. So we have the half circle. Okay. But now I'm going to write the equations in spherical. So we know that the equation of the cylinder in spherical is rho equals root of 3 over sine of phi. And the equation in of the sphere, right? The equation of the sphere is rho equals 4 cosine of phi. So what are how do we find the bounds here in spherical? So you have to draw. You're going to draw rays now. So spherical, remember, in this from this perspective, behaves like the polar coordinates. So you draw rays to find the bounds in this case. And in spherical, the dv, if you don't remember, that becomes rho squared sine of phi. So you put, right, you get rho squared sine of phi d rho d phi d theta. Okay, so there are bounds for rho first. And okay, what are the rho bounds here? If you follow the rays, they enter through the like yellow line, which is root of 3 over sine of phi. And they exit through the circle, which is 4 cosine of phi. Okay. Theta is the same as before, so it's still from 0 to 2 pi. So in fact, if you want, you can complete that one. So like the only thing that we have to figure out is the bounds for phi, which is when which is like what are the angles between which angles phi goes in this region. Okay, so there are two ways to do this. Like I'll try maybe to show it to you in the more like trigonometric, like picture way, instead of like just playing with some trig identities to make it a bit more interesting. So okay, so if you remember, like phi is an angle that starts at the North Pole, right? Phi starts at the North Pole and it moves towards the equator, right? So let's zoom in this picture to better. I'll exaggerate everything a bit so that we have a bit more room. Okay, so okay, so phi is 0 at the North Pole, and it start and it it will increase. So there's an angle phi1 here, right? That will be the lower bound for our situation, and then just a bit exaggerated, but there is going to be if you draw the circle again and the line. Okay, this is gonna be a bit too much. Let me draw it closer to the circle so that it's a bit more clear. If you draw it here. Yeah, oh, it looks good. Then, so V1 is going to be this one, and then the angle increases until you get to this other value, which is V2. Does that make sense? So those are the two angles for phi, and we need to find which they are, what are the values for them. So one way to do that is just like you have to find, well, you have to find these intersection points, right? So you need to find like the coordinates for these points. If you want to do this geometrically. So where does this happen? This happens when the two um, you know, so we need to find this point and this point, this point and this point. Okay, well, I mean, they're the same, but let's see, when do you, when are those values? The values are when the two equations intersect. So you have to equate the equation of the circle, which is r squared plus c minus 2 squared equals 4. Right, that was the equation of the circle, and the equation of the line is r equals root of 3. So whatever these points are, you know that the first coordinate is root of 3, right? That's like so we're just trying to find the value for z. So when, substitute this into here, so you'll get 3 plus z squared minus 4z plus 4 equals 4, right? And so, okay, the 4's go away. Right, so you get z squared minus 4z plus 3 equals 0, right? And can this be factorized in a nice way? Right? Is that okay? Yes. So z equals 3 or z equals 1. So the 1 obviously should be this one, and the 3 should be this one. Is that okay, everyone with me? That makes sense? Uh, and once you have that information, you have everything that you need to complete the right triangle, because what is the height? Let me put it with a different color. So for the first triangle, what's the height of this? Like, what's the length of this side? This length has length. One of these sides is 3, and the other side is like the gel, like this separation, which is root of 3, right? So you can say here that the tangent of V1 is opposite divided by adjacent, root of 3 over 3. So V1, I don't think, is this a special triangle? I don't think so. So it's just like the arctangent of this, whatever that is. So yeah, I thought I changed a few minutes ago the numbers so that these would come up nicely, but then the price was that the angle is a bit so that is the first angle. And what is the second angle? So you now have a right triangle for the second one where you know, this is root of 3, and then the vertical side is now 1. So the tangent of V2, I mean, you could have used sine or cosine, like, but it's easier with tangent just because you have the two sides already. So the tangent of V2 is like the opposite divided by the adjacent side. Oh, and so is this one is arctan of root of three is something. Is that a special angle? Is that pi over six or pi over three? Pi over three? Oh, the other one is pi over six? Oh, good. Oh, perfect. So, huh, okay, good. Let's do this. So it's one half, right? And then pi, this is seven, right? So root of three over two. But isn't this like, oh, because it's, oh, this is one arctan of one over root of three, right? And if you rationalize it, okay, so this is one of the advantages of rationalizing things. So like, oh, okay, so it wasn't that bad, so I didn't screw it up. So one is pi over this, so this would be pi over six, right? Yes, and the other one and then is pi over three. Perfect. Okay, so it wasn't that bad. So it looks a lot better. So it's like the p goes from pi over six to pi over three. There's a more algebraic way to find the angles, which let me just tell you quickly which it is. Like the other algebraic way to find the angles is like you say, well, the intersection must occur when the equations are the same, right? If you look at them from the spherical coordinates perspective, you must equate these two equations. So you get that 4 cosine of phi equals root of 3 over sine of phi. So you get that 4 cosine of phi sine of phi equals root of 3, right? But there's this identity that 2 cosine sine equals sine of 2 phi, if you remember it. Like there was this identity. So this can be rewritten as 2 sine of 2 phi equals root of 3, or sine of 2 phi equals root of 3 over 2. And from there, like just, I mean, you will find these two values. But that does require remembering this, so that's why I kind of try to avoid it, like, as a solution to the problem, so that you can see, you can do it more like, in terms of the picture. But yeah, you can, in principle, figure it out if you solve this equation. So, that would be the other alternative way to solve this problem. But I do prefer this one because it's more concrete, you draw the triangles and you find everything from the triangles. Is that okay? Is that making sense? So I think this one illustrates like in a good way why sometimes spherical coordinates is harder than cylindrical, because finding the bounds in cylindrical is relatively straightforward, but finding the bounds in spherical can get more tricky because of the angle stuff. So the angles, like finding the angles here is not impossible, but you do have to kind of pay more attention to like the geometry of the problem. Whereas in cylindrical, it's easier just because everything like the bounds are just kind of more like Cartesian bounds. So it kind of is more easily readable from the diagram directly instead of like playing around with this some trigonometry stuff. Okay, but so that's how the integrals would look like uh, in both of the perspectives. Is that making sense? Okay, so now, if you remember the diagram that I did at the beginning of the class, okay, this is kind of like a local max. Now we're entering like an easier part. So now we're switching topics a bit, and we're going to talk about doing other types of integrals. So far, the integrals we have studied on the course are like double integrals and triple integrals, right? So far. Um, the integrals we have done. Are double integrals. Double integrals are regions for regions on the xy plane, right? So like a region like this, and triple integrals, which are for regions in space, right? So that's how they look like. And now there are two different, there are two other things we can do for integration. Um, so the first one is that we can do integrals over curves. So now, like what we're going to analyze is like, we'll do integral along curves. So like imagine I give you like a wire, a curve is like some sort of wire in space. So I want an integral that takes place along the curve. Okay. And the other thing that we'll do, which is the last topic, and that is a bit harder than doing the curve stuff, is integrals along surfaces. So so what is an integral about? What is like a surface? Like, the surface could be like a paraboloid or, okay, so, or let me just draw something like this, like that looks more like a blanket. So like I give you a surface in space, like a blanket, and I want to do an integral that takes place on the surface, which is different from like the region, which would be different from the region like bounded by the surface or something like that. It's just like on the surface itself. So for example, if the surface is like a sphere, by that I mean like an integral over the sphere, not over the ball, like bounded by the sphere. So this is a bit different from like the triple integral. So like not to be confused with that. Okay, so today what I'll start in the first part is it's relatively easy. It's just how to do the integral over curves and of functions, and then on Monday we'll talk about integrating vectors along a curve, and that corresponds to what the concept of work in physics. So let's just discuss first how to do the integration. So what we'll do today is how to integrate a function along a curve. So uh, let me draw a curve. Let's say you have a curve here. This is a curve. Remember from the beginning of the course, for us curves, the way we're thinking about curves is that they're kind of like the position of a particle that moves on, in time. So we had discussed this thing about parameterizing a curve. Parameterizing a curve just meant that you would give like the position vector of the curve in terms of time, right? So if you had a point x, y, z on the curve, right there, like a parameterization of the curve. A parameterization of the curve consisted in giving this position vector as a function of time. So remember, a parameterization of the curve is just to give the position vector as a function of time. So one type of problem that you could think of is the following. Like if you have a curve, which now think of it as like a physical object, so it's like a piece of wire or something like that, then you could ask, well, what's the total mass of the wire? That is like a reasonable question to ask. How like, how heavy is a wire, basically? Um, or another one, I don't know if you have seen this, like maybe this one looks a bit more normal, familiar. So if you have like a mass, like a point mass, right, at a certain height, it has a gravitational potential energy, right? Which is like mgz. Well, usually you call it mgy because usually the y-axis is the vertical one, but if now the z-axis is the vertical one, like that's the gravitational potential energy. But that's for a point, right? But if you have a wire, right, what would be the potential gravitational potential energy of a wire, right? So the way you would like to think about the wire is built out of many, you know, tiny pieces of points, right? And for each of these points has like a potential energy, and you want to add up all the potential energy of all the points along the wire, if that makes sense. But to add it up, you just have to do like an integral. That's plausible. So that is like the typical way to compute, like, like the potential energy of like an extended object. You break it into pieces and then you add up the individual energies. The same with the kinetic energy if you thought that this is moving in time. Okay, so that is one of the reasons why it makes sense to try to integrate functions along curves. Like, because if you think of the curve as being made out of like tons of tiny particles, then you're kind of like just integrating, like adding up the properties of those particles. Okay. Um, so I want to integrate a function f. I want to integrate, so this is my goal, to want to integrate a function f along the curve. Which I'll, let's call this curve C. So for example, yeah, this is supposed to give you things like the total mass, or it could give you like the total potential energy, which is what I was discussing a couple minutes ago, potential energy, or like the total electric charge as well. That's a very common problem, as a kind of fun problem to do. Energy, total electric charge. So okay, that would be things that you can try to integrate. So the easiest one to think about is maybe if you wanted to find the total mass of the curve of the object. So think of the curve again as a wire, and and then let's say think of the function f as the mass per unit length. Okay, So it's what people refer to as a density, like a mass density. Usually density, maybe you have seen it like mass per unit volume, but there's like variations of that. So like this would be mass per unit length. So again, the way to think about the total mass of this object is like to chop off the curve into pieces. So I'm breaking it into mini segments, right? Right. So like if you look at one of these segments, it has some small mass, some tiny amount of mass, which I'll call delta M because it's small, right? So you think, oh, this has some mass, small mass. But would be the mass? Like it would be, you know, it would be the density, which is the mass per unit length, times the length of this piece of the curve or the wire. Usually, I don't know if you remember that, but we saw that a while ago when we had these problems about finding the arc length, the length of a curve. That is what people usually call delta S. So delta S, where this is like the length of this piece of the wire. So the total mass is kind of like what you would get by adding up all these smaller pieces of mass, which means doing an integral. So you would like to say, oh, well, the total mass should be something like the integral, like the sum of all these like delta m's. But delta m is f times delta s. So it's kind of like the sum of all f times delta s. But the proper way to do that is like as an integral. So it really is like an integral of the function times ds. That's like a calculus version to write that. I'll put the bounds in a bit, like there's nothing to worry too much about. And so the question is, how do you find the length, the length of a curve? And that is where the parametrization comes in handy, because like the distance traveled along a curve is the magnitude of the velocity vector times the amount of time. Okay, so there was this formula for the arc length. Um, but like if you think about it in terms of a car, it's like how much distance, how much did you travel from from this point to this point? It's like, well, basically like the speed of the car times the amount of time. That's more or less true when the amount, like everything is infinitesimally small. This gives you f times the magnitude of the velocity vector times dt. Okay. So here, this v is like refers to the velocity vector. So here, and so that the magnitude is the speed. And that's basically the formula we'll use for integrating a curve. So if you want to integrate a curve, what we'll do is you multiply the function by the speed and integrate that. That's essentially the formula. So let me write that down. So if we do integrate along f along a curve. So here are like the steps that you have to do. You have to parameterize the curve. So step one is to parameterize the curve. Which means to find the position vector in terms of t. And then you find the speed of the curve. Which is the magnitude of the velocity vector. So that is the actually t squared. Okay. Then the third step is to rewrite f in terms of t. In terms of t. And the final step is to integrate here from the initial time to the final time. So, okay, so let me do an example to show what I have in mind. So let's say that I want to integrate, so consider the curve. Maybe. Even to make it easier. I'm just trying to really find different numbers. Yeah, I think this one will be fine. I'm just trying to make the numbers kind of nice. Okay, so there's a good point also to mention, the sense in which the exam is cumulative, the final. So the majority of the problems are kind of on the new stuff. But as you'll see, like from the practice exams once I post them, but there will be problems on the new stuff that sometimes will have like a part that more or less would correspond to things you would have done for either the first or the second exam. So for example, here, one of the first things you have to do is parameterize the curve. And parameterize the curve, if you remember, was kind of like a typical exam one problem. So in a sense, like the certain problems of the first or second midterm are kind of like integrated into the new problems. So it's not that necessarily you would see like a problem on the final that's just like parameterize the curve because that already has been tested. It's just that now parameterizing the curve is required to actually do the problem you care about. And so it becomes kind of like part one of a larger problem. So if you look at this recipe, right, step one is to parameterize the curve. To parameterize the curve. So what does it mean to parameterize the curve? Again, the curve, I should actually draw it if you like. So you have this you have a plane, which is a bit difficult to make here, but in fact, like it's better if I don't draw the axis. So the idea is that you have a plane. It's actually better this way. So you have a plane and then you have a cylinder. Right, so when you intersect the plane with the cylinder, you get like a curve, on both of them here. Oops, so they like. This is the curve the problem is referring to. Okay. So the curve is the intersection of these two surfaces or right. Um, and if you remember, the thing that we did in the first exam is like whenever we saw something like x squared plus y squared equals a number, that it was like a indication that you should use a cosine and the sines, right? Because it's like a circle. So the parametrization is that here that x equals cosine of t and y equals sine of t from the second equation, right? Everyone remembers that? Does that making sense? And once you know that x and y are those things, right? Then you know what z is supposed to be because z equals y, right? So that forces like the first equation forces z to be y, which is sine of t. So um, the parameterization of the curve is cosine of t, sine of t, comma sine of t. Where t goes from where to where, 0 to 2 pi, right? Because it's like you're looking at this circle, which is this curve is exactly on top of this circle. So the t goes from 0 to 2 pi. Is that okay? Is that making sense? Kind of. What's good? Um, okay. Yeah.
Could I ask you size here and why the approximate here?
Yeah, that also is fine. It's more conventional to do it this way because then like the curve, like the circle is moving counterclockwise if you plot it, so that's kind of like the standard convention, but yeah, you can flip it around, yeah. Do that also, that's also fine. Cool. So that's step one. Step two is to find the speed of the curve. For that, you find the velocity vector and then its magnitude. So what is the speed? Sorry, what's the velocity vector? Is the derivative of position with respect to time, so it's negative sine of t, cosine of t, cosine of t, right? And then you take the magnitude of this for finding the, you know, the speed. So the speed is the magnitude of the velocity vector, which is the magnitude of this thing. So again, it's Pythagoras theorem. You square each entry of the velocity vector, so you get sine square of t plus cosine square of t plus cosine square of t, right? And sine square plus cosine square is 1, right? So you get the square, like the best, like the most I'll try to simplify this is just to write it as 1 plus cosine square of t. Okay? So that is the formula for the speed. So let me try to put this in boxes. So step one is here. Step two is in here. And then step three is to rewrite the function in terms of the parameterization. Okay. Because again, what's can be confusing a bit about this is that the integral is taking place along the curve. So you are integrating the function along the curve, which means that f, so the function is that thing, 2x squared plus y squared over 2 plus z squared over 2. But along the curve, x, y, and z become the thing that the parameterization tells you they are. So along the curve, this is x, this is y, and this is z. So you can replace that in terms of like t. So oops. Along the curve, x squared is cosine squared, right? So you get 2 cosine squared of t. The other one is sine square of t over 2. So sine square of t over 2. Okay. So that is the fun, which again can be simplified a bit, so. So this gives you. Okay, this is cosine, two cosine square already, less cosine square plus cosine square, you'll see why. And sine square plus sine square equals sine square over two plus sine square over two equals just sine square. And then this gives you what? It gives you this, there's a one here, so you get cosine square of t plus one. So that is what the function looks like. That makes sense. Okay. Okay, so that is a function, and then the idea is to integrate. So the difference with the curve is that when you integrate along the curve, you don't integrate the function on its own. You integrate the function times the speed. So that's like what you have to be careful about, which is what I erased here, but I'll rewrite it as step 4. Because you could say, oh, this is like a function of t, so that's ready to integrate. But no, it requires a factor of the speed. So what you do is so step 4 is to integrate. So in this case, like the curve goes from 0 to 2 pi, the function is cosine square of t plus 1. The speed is root plus cosine square of t plus 1 dt. Okay, I chose things so that they would be the same, so that the square root goes away. So otherwise, it's complicated to integrate. So it's not like a coincidence. I chose a function on purpose so that this would happen. So they're the same factors, so like the square roots, you can get rid of them. So you're just integrating like the integral from 0 to 2 pi of cosine square of t plus 1 dt. Okay, for something like cosine square, I guess I would give you like, again, like the double angle formula or whatever. It's not too complicated. Like there's a formula for cosine square in terms of like cosine of 2t. It's like 1 plus or minus cosine of 2t over 2, something similar like that. So anyways, like this, which I would give you, I guess. So this integrates to pi, that's fine. And the other one integrates to 2 pi, so you get 3 pi. But the important thing here, like the important thing of this example is that when you do an integral on along a curve, you don't integrate just the function. You have to integrate the function times the speed. That's like the important thing to remember of everything that I have said. So to do this, like you need the speed first. So that's why we have to parameterize the curve. Okay. What is that okay? Does that make sense? Any questions about this? So what we will do next time is a lot more interesting. This is kind of like like it's actually a relatively simple thing to do because they're ordinary single integrals. Like there's not even like a double integral here. It's just like a regular Cal1 integral of a function. It's just like the only extra thing that you have to do is parameterize the curve. What we will do next time is something a bit more interesting, which is how do you integrate a vector along a curve? Okay. So let's say if I give you a vector, just to finish quickly, if I give you like a curve and I have a vector here, how do you integrate this vector along the curve? And what we will do, because this is a vector, right? What we will integrate is not, you don't want to integrate the vector on its own. By analogy, what we will integrate is the, instead of like f times the normal B, what we'll do is integrate the dot product between F and B. Because the dot product gives you a number. So that's the easiest way to produce a number when you have a vector, take a dot product. And this we will interpret later as like the work that would be done on a particle if you think of this as like a force. So this is like the formula for force. If like, I'll show that to you next time. But we'll talk about that and whether the work like force is conservative or not, and what does it mean for a force to be conservative, that there's a potential function. So we'll talk about all those things next time, which is a bit more interesting than this. So. Stop here.